Hello, welcome to the Area Solutions channel. In this video, we shall be presenting engineering mechanics 2, and more particularly, we shall be solving an example that borders on moment of a force. So quickly, we're going to walk through this problem, and we're going to start first and foremost by trying to determine the moment of the 213 Newton force about point A. And to solve this problem, basically, we know that moment is the cross product of the position vector and the force both in their component forms. So first and foremost, we're going to be looking for the position vector of the force, which is displacement from A down to where the force is. That is from A to B, then through B to C, and from C to D, and then to the point where the force applies. Then after that, we need to look for the force itself, which is the 213 force that is acting at the point D. So if we can take this force to the component form and with the position vector, we can then look for our moments. So first and foremost, let's determine the position vector R, which is equivalent to, like I said, the displacement from A to B, which we know is just 200 meters and is in the direction of the x-axis, so it's going to be plus 200i. Then we have the displacement from B to C, which is against the y-axis because it's coming down, so it's going to be negative of that value, and in this case the dimension is 120 millimeters, so we have minus 120j. Then so we have the displacement from C to D along the z-axis, which is also the same in the same direction with the z-axis, and the dimensions are 40 mm because it's same in the direction of the z-axis is going to be plus, and the 60 mm in the direction of the z-axis is going to be plus 60k as well. And finally, we have another displacement from the points, as we can see, to the exact points where the force lies, and that is just 20 mm and is in the opposite direction of the x-axis, so we have minus 20i. So if we simplify this further, we're going to get our position vector to be 180i minus 120j plus 100k. Then next, we need to look for the force itself. We know the force is 213 newtons and is acting on the YZ plane. So basically, we can bring out that plane and we see the force acting on it with its coordinates y and z. The force makes 35 degrees with the y-axis. So basically, because adjacent angles are equal and complementary, so we can bring back the 35 degrees down this way. Then also we have that the force has component forms, which is Fy to be equal to minus F, that's the force, times cos 35, and also another component in the z-axis, which is going to be minus F sine 35. We must note that the reason these forces are negative is because they are acting in the opposite direction of both the y and the z-axis respectively. So if we bring that back into the force that we are looking at, we have 0i because there's no component of the force in the x-axis, and we have the Fy, which is minus 213 times cos 35, and we have the Fz, which is minus 213 sine 35k. So basically, we have our values of forces in its component form as shown. So let's not forget that the goal is actually to get moment. We've determined the position vectors. The position vector of the force, we've determined the force in its component form. However, a formula for calculating moment to be R cross F, which is the same thing as finding the determinant of the matrix that has this form. Some other persons can use a formula for moment that is derived from this matrix that we can see. But basically, if we put back everything into the matrix form, that's we put the position vector and we put the force into the matrix, we can find the determinant of this matrix as shown. Then we can get our value for moments in Newton millimeters. So to take our values of moments to Newton meters, we just divide through by 1000. So we get our moments in Newton meters. as shown, and we can find the magnitude of this moment by squaring all components and summing them together, then looking for the square roots. So if we do that, we get something like this, and when we simplify, we have our moment to be 50.01 Newton meters. And that's our answer. So it's quite easily determined. But however, the question can come in other form. For instance, we can be given the moment of the force P about point A to be 50 Newton meters and asked to determine the force P. So this is just the reverse of that other question. The first one, we're given the force, we're asked to look for moment about A. In this case, we're given the moment and we're asked to determine the force. It is the same procedure. Of course, you start by looking for the force components. Force components, you just bring it out as I said earlier, and you try to take it into the different components. Here we have P cos 35 for y-axis and we have P sin 35 for the z-axis. And remember, our s-axis remains 0, so we can get our component form to be 0i minus P cos 35j minus P sin 35k. So recall that our moment is the product of r cross f. The position vector r remains the same, 180i minus 120j plus 100k. Then we have our force determined as shown. Remember our formula, just to call your moment, and you put back everything into the matrix and you simplify. In this case, you are simplifying while retaining the value of P. So if you simplify further, you get this value of moment in Newton millimeters. If you divide by 1000, you get the moment in Newton meters. Remember our force was given in Newton. And we have our moment the magnitude of moment, which is 50 Newton meters, to be given with this formula wherein you square each of the components of the moments. You add them up and you find the square root. So if you do that, you have our moment to be as shown, and if you equate them, because our moment is given as 50 Newton meters, we have what is shown. And if you simplify, at the end of the day, you have our force P to be 212.955 newtons, which is also equivalent to 213 newtons. I believe this is straightforward. The difference between this problem and the first one is that one, you're looking for moment, the other one, you're giving moment and you're looking for the force. So this is also quite easily determined. And there could be several other scenarios. You could be asked to look for the moment about B. You could be given the moment about B and asked to look for the force. The force could take other forms as well. This is just a planar force acting on a 3D system. The force could be a 3D force, and so on and so forth. So regardless of the scenario, the procedure is the same. You find the position vector, you take the force to its component form, you cross them up in a matrix, you simplify, and you get the unknown. And I think that is that. Thank you for your time. I hope the video was helpful.